But my talk today is really about climate applications, and I think a lot of the things I'm speaking about can be very generalised to thermal data and actually all satellite data, but there is a definite focus on land surface temperature remote sensing because that's where my expertise is. So I'm going to talk about three parts of my presentation. Firstly, I'm going to give some example climate applications for land surface temperature data, or LST, focusing on observations. And then I'm going to talk about the relationship between LST and 2-metre air temperature, which is quite a hot topic and something Anestra and Jem wanted me to cover in this talk. And then finally, talk about some generalised things to consider when using any satellite data for climate applications. So I'm going to start with this, following on from Sue's talk. So this is a tool that we made with the Institute of Environmental Analytics. The link is at the bottom there. And one of the applications for this tool was to showcase land surface temperature data and how it might potentially be used for surface urban heat island applications. And you can visit the link yourself, but I've taken screenshots here to avoid the risk of having any problems interacting with it during the presentation. So the first thing is that satellite data are a really great communication tool. And what we do in climate is we don't focus on one specific image, but normally we take an average over a longer time period. So we look at what typical conditions or climatology, if you might call it. And in here, we've used 16 data. This is a number of years ago we made this tool, but we used 16 years of data from Modus Aqua, which has a local overpass time of 1:30 a.m. and p.m. So you're really seeing the real heat during the day in this example here, which is the day. You can change, this is an example of 44 cities in China. You can select the city and also the time period and the season and whether it's day or night as well. And there's various other things you can do with this tool. And the example, as I said, shown here is summer. So we're seeing some really high temperatures. You can see there, if you click on the map, as a temperature and LST of 42.4 degrees for this mean sort of period between 2003 and 2018. And the idea of really one of the applications for this tool is to do exactly what the gentleman asked there, which was to map which areas of cities are hotspots potentially. And there are a number of studies that have shown that hotspots can be linked with increased mortality. There was a study done a few years ago over Philadelphia, and they actually found that the hottest places in Philadelphia were associated with the poorest living conditions and the highest rates of mortality and morbidity. So there's a lot of interest in this kind of thing. So one of the ideas here was to see whether we could do this with satellite data averaged over these time periods, as I say. So once you can zoom in and you can plot there like a Google image type map to see exactly where these hotspots are, in the squares you can see there are the individual 0.01 degree MODIS pixels that we're using now. You can actually zoom in closer than I've shown here and actually read off the values of satellite LST. Another feature of the tool is to be able to look over different land cover types. So on the x-axis, we've got a variety of land cover types there, and then the mean LST is shown by the bars with, I think it's a standard deviation to show this sort of typical range there. And you can see straight away that urban stands out as a much warmer area compared to the vegetated areas. Also bare and sparse, that kind of tan coloured bar there is also very warm, but urban is the warmest temperature. There are some things to think about, of course, when you're thinking about LST over urban areas. And Sue has highlighted many difficulties with doing this with satellite data, that we have many uncertainties on what materials they are. So we're often getting the emissivity wrong. And I think you've already heard about how important emissivity is for LST calculation. And it's very difficult to know exactly what the urban environment is made of. So there are a lot of assumptions made in these data, but I think there's still some useful things that we can find from them, even with these assumptions and errors in those data. So for example, if we're comparing here, what we've got here, the background is the period 2003 to 2010. And then that circle there is 2011 to 2018. And if you look on that circle, you can see the warm. If I flick between them, you can see that the earlier time period is cooler than the later time period. We don't know why this is. It could be climate change, it could be urbanisation, it could be change of materials. This is Beijing. But there's a clear signal there that we believe could be potentially useful for looking at urban warming and urban changes and what we can do in the future to mitigate against urban heat hotspots. So you've heard from Sue, and so I did plan this presentation following on from Sue's talk, but if you're staying on for the LSTCCI workshop, we have several talks on urban applications for LST data and also several posters as well, if you're staying on with us for the next couple of days. So one of the other areas, there's lots of use of LST data, is to look at surface temperatures globally and regionally. And traditionally, we've done this for many, many years, centuries, in fact, looking at station observations. And this is a map from one of our Met Office data sets in collaboration with the Climatic Research Unit in the UK. And this is a gridded product here, and it's actually 5 degrees spatial resolution. And that is limited very much by the density of the stations that we have to interpolate, to create this data set. And consequently, you can see there are gaps. But it's still very useful, and we can see, and this is from the IPCC report, these kinds of plots here, the very famous hockey stick increase in surface temperatures. But there are lots of areas which are not observed, and I think one of the real uses of LST data is that we can see areas that we can't see well with with station data. And actually, also, even where we do have station data, sometimes they aren't at sufficient density to find out the information that we actually want to know. The bottom there is a map of global stations from NCEI in the States there. So one of the things that we've done, and this is a paper that I published with colleagues from University of Leicester in 2017, and this was using a climate data record created from the ATSR series, starting with ATSR2 in 1995 and going through to AATSR in 2012. And what we like to do in climate is we like to do anomalies, because what we do is we have a baseline period, what's the climate kind of normal, typical conditions, and then we subtract that from what we're actually seeing. And that's what we've done here. So CRU-TEM4 is a gridded station data set, and those are anomalies. And we've done the same with the satellite data, referenced to the same baseline period, and then compared them. And as you can see, there is a very good correlation, I think 0.9 or so, between those two time series. And actually 90% of the LST anomalies from this satellite climate data record fall within the CRU-TEM uncertainties, which is that blue shading. And so straight away, we can see that there's actually a very similar signal coming from the LST data compared to 2 meter air temperature data. So of course, this has fueled a lot of interest in trying to use LST to predict 2 meter air temperature and things like that. And there's a lot of potential for synergistic use of these two types of observations. But as I'll come on to later, they are very, very different, and that's crucial to remember. So the other thing we're doing, this is current work that's being done by Josh, who's here, Josh Lannan today, and he's talking about this more tomorrow, is the use of LST data to complement 2 meter air temperature extremes. So again, we've got station density in that top plot there. And then we provide this gridded station product of extreme, moderate extremes. It's called HADX3, it's cited in IPCC. And we put time series, and it's very, very useful. But as you can see, there are big gaps in the data, and there are many regions which are very heavily interpolated. And we know that these areas are not being captured accurately by the station observations and the data that we're producing. And so this test that we're doing here is to see how well we can create a sort of satellite data set to complement what's going on here. And of course, one of the crucial things with satellite data is that we can provide this at much higher spatial resolution. Because the HADX3 data set, as you can see there, is nearly 2 degrees by just over 1 degree. So it's quite a coarse grid. So I've got Josh is talking in more detail about this tomorrow afternoon. But what we're trying to do here is we're using a set of indices which have been designed for 2 meter air temperature. We're seeing how well they work with LST data. Some of them work quite well, others do not. You can imagine threshold-based indices. Say, for example, summer days, I think it's over 20 degrees or 25 degrees. And obviously LST is very different. So we're not getting the same triggers there. But some of the indices are giving us very good complementary information. And this is an example from the AR6 assessment report, the IPCC region in Northern Europe, which shows time series of percentiles. So this is exceedances of percentiles of the distributions of LST in 2 meter air temperature. And you can generally see, so the top one is exceedance of Tmax 90th percentile, then it's below Tmax 10th percentile, and then it's minimum temperature 90th and 10th on the bottom two panels there. And you can see generally that these time series complement each other very well. There are lots of agreement where we can see, if we look at these examples here, we've got nice extreme events which are being captured similarly by both data sets. But there are also some examples where we have some differences. And this is ongoing work that we're trying to understand. We also think there's a lot of value actually in using LST as an index by itself. LST is much more sensitive to leaf temperature, for example, and so may be very useful for crop health, we know it is, but also for things like pests and predators of those pests as well. So we think actually LST-based indices are really worth pursuing, as well as those that may be indicative of 2-meter air temperature extremes. So coming on to this now, this relationship between LST and 2-meter air temperature. So this is looking at anomalies. So this is where we've got a baseline period of a number of a couple of decades, I think, or so, where we've taken daily values, and we've created a distribution of those anomalies. So the differences from the normal state of the climate. The top example here, the top two on the left is minimum temperature, on the right is max. The top two plots show the LST CCI data set, which you'll hear from in a minute from Mike, is for Modus Aqua. And we can see that there's quite good alignment between those two distributions. So the red is the LST and the blue are the station anomalies. And then the bottom two plots show the same, another LST CCI data set, but this time based on microwave LST, which is at about 6 a.m. and 6 p.m. And we were quite surprised to see how well these anomalies line up. And so actually, this is a lot of evidence to support the use of LST anomalies as indicators of anomalies in 2-meter air temperature. So we think there's a lot of promise in particularly pursuing that aspect of using LST data. And the reason for this is because when you go on the daily timescale, diurnal timescale, there are a lot of differences. So this is from a paper I published back in 2016, where I only used in situ data. So this is in situ, I think it was 1-minute temporal resolution, LST with a radiometer, and 2-meter air temperature data co-located in time, space exactly. And then you can see the time series for different stations over a course of a day up on the top there on the right. So that first plot, Niamey, which is Niger, I had to look really hard for that example. It's what we think of a typical diurnal cycle for LST in red and 2-meter air temperature in orange. I had to really look very hard for that, because most of the diurnal cycles look like the other plots on there. And I wanted to pick some of these things out that affect that relationship between LST and air temperature. Wind speed is one, so that's shown in green on the plots, and cloud is shown in blue. And if you look at the top panel C, which is the Cape Cod example, you can see an example there where we've got mostly clear, fairly low wind speed day, but then we have some cloud that comes over in the afternoon. You can see that LST drops immediately by sort of almost 10 degrees and actually aligns then very well with the air temperature. So you can see the difference when it's a clear sky for this site in Cape Cod, Massachusetts. There are very large differences between LST and air temperature, but then this can be really affected by cloud and wind speed. There are other examples on there as well, on panel D, for example, where we've got some wind speed effects going on there, where we have much higher wind speed in the green, and that makes the LST and the air temperature, that mixes the air, mixes that heat transfer, and so you get this very, very close relationship. And the same thing happens under cloud, and there's other examples there. The bottom right-hand one's an interesting one, because actually the maximum air temperature and LST occur at night. So these, on the x-axis is actually local time. It's not a UTC, it's a local time. So you actually have air temperature and LST peaking during the night, and the low is actually during the day, which is interesting. And that's probably, or almost certainly, because the different weather system has moved into the area and changed this relationship of when these maximum and minimum occur. So in the paper I reference here, we also look at things like vegetation, which I'll come on to, but snow cover, and surface roughness, which influences that turbulent mixing and the heat exchange between the surface and the atmosphere. So this is a really interesting example with vegetation. So this time series here is minimum temperatures. I'm really interested in the bottom one, actually, the maximum temperatures. So the red line here shows the difference. It's the LST minus 2-meter air temperature. Green is wind speed, blue is cloud, but this red line I really want to focus on. So when I saw this, I thought, what on earth is going on? Because you have these massive jumps from fairly similar LST air temperature to a very big difference. And I contacted the people who run the site, and they said, oh yes, we mow about once a month, every 6 weeks. And that's what I think is going on here. I think when you get to this point, you've got vegetation, grass, growing, and the air temperature and LST are very similar, then you've got mowing. And because it reduces the density of the vegetation and exposes more bare soil, the LST goes up, whereas the air temperature stays very stable. And you can see that sawtooth effect there is probably, we think, due to this mowing activity. So it's very important to consider these things when you are thinking about the differences between LST and air temperature. The other major difference as well is the timing of the maximum and minimums, and we've already seen that from those diurnal plots in a couple of slides ago. If you focus on the top plot here, I've added the bottom in context, but the top one is basically the density of times when these occur. So the solid line is LST min, the dashed blue line is T min, sorry, and the red line is LST max, and the dashed red line is T max. So the yellow band there is when sunrise occurs, and the orange band is about solar noon. And what you can see very clearly is that the LST min and T min generally occur around 6 a.m. or just before sunrise, basically, around that time. And they occur at very, very similar times. Whereas when you look at the maximum temperatures, you get a very obvious difference. We have LST, which generally peaks if it's cloud-free at solar noon. And whereas air temperature takes much longer to react to that heating transfer and tends to peak in the middle of the afternoon. So this is really important. So it's very difficult, I think, to predict instantaneous air temperature from LST. That is probably impossible, in my opinion, because of these complex relationships. And when we look on a global scale, we can see that there are very large differences. So these maps here are using the same data that I showed you at that time series from glob temperature with LST, minus another data set from CRU here in the UK, showing global differences on a seasonal basis between LST night and T min on the left, and on the right is LST max and T max. And you can see that there are very large differences in many parts of the world. And this may be due to errors in the data, of course. There are errors in this is an interpolated air temperature data set, almost certainly errors in there. And also the LST data will have errors as well. And Claire is going to talk about uncertainties later. These are very important to consider when you're looking at your data. But I just wanted to include this plot to show how much that relationship does vary and how difficult it is to predict LST from 2 meter temperatures from LST. There have been many studies that tried to do this, and I think it's really difficult. I've tried it myself, it's very difficult. But I think, in my personal opinion, I think that anomalies are probably the way forward. We see a very similar signal coming from those anomalies, especially over course of time periods like monthly temporal resolution. And in my personal opinion, this is probably a better approach to focus on rather than trying to make LST look like 2 meter air temperature, because they are very different. So finally, I've got a few slides here just on things to bear in mind generally when using any satellite data for climate studies. This is not an exhaustive list, but in my opinion, are some of the key things to think about. I'm going to talk a lot about stability because that's really important for climate. So these plots here are not mine. They've referenced there from RM at the bottom right-hand corner of the screen. So this shows satellite overpass times and how they change. There are many stable satellites, but there are also many unstable satellites. On the left-hand side, you can see many of the NOAA platforms which carry AVHRRs, for example, which we use for LST. On the right-hand there, we've got platforms which carry microwave sounding sensors, which you can use for LST. And you can see that most of these drift. The Aqua platform is quite stable. Metal Pay and Metal B is very stable, but many of the others adrift by many hours over their lifetime. So you can't just take a time series of LST from AVHRR and use it for climate, because LST has a very strong diurnal cycle, as I've shown. And you're also thinking about adjacent orbits here. There are about 14 orbits a day as well. So there's many changes that are happening when you're looking at that relationship over time. And what we've done in LST-CCI, which Michael might will mention shortly, is we've used these two sensors for LST in the microwave. And I'm going to show you what the consequence of that orbital drift is on LST. So this is from microwave data. So that's these two sensors, F13 and F17, which look, compared to some of the others, one of the more relatively stable sensors. But you can see the LSTs all over the place. It varies quite a lot, and that is because LST has a strong diurnal and seasonal cycle, of course. So what we tried to do in LST-CCI is to create a correction to try and harmonise these two sensors. And you can see that this is from my colleague Carlos Jimenez, who's will be speaking tomorrow, has done a very nice job here. And you can see that they align much better after he's applied this time correction to the data to correct for that orbital drift. It's a very difficult problem with LST. Something else to think about as well is instability in input data. This is something that's been discovered relatively recently. This is an emissivity data set. Many of you may have heard of it already. It's called CAMEL. There's version 2 on the left and version 3 on the right. This is a global plot of the average emissivity produced again by my LST CCI colleague, Sophia from IPMA, who'll be speaking again tomorrow. And you can see that this data set is very unstable. So, of course, when you put this in your LST retrieval, it's going to be unstable. And that's what we find in this plot here. You can see the effect that Sophia has found on MODIS LST. This is from Aqua, I think. And you can see how this change in emissivity data has propagated through the LST retrieval. And you can see that there are non-climatic artifacts in there. And it's really important to notice that. And in this case, Sophia's compared the data to ERA 5, which is a reanalysis. So reanalysis is essentially a numerical weather prediction model run in delayed mode, run in a historical mode. And so it provides a very nice data set, but that is also includes non-climatic discontinuities because the data that go into ERA 5 changes over time. So we have to be very careful when we're thinking about stability. The ERA 5 is a good reference, it's very useful, but it's not completely stable itself. So I just want to make this point, the CAMEL 2 emissivity database, if anyone's using it, be careful. We think it's over arid regions and sub-arid regions in particular where this problem is occurring. And it's used very widely. It's produced by University of Wisconsin and NASA. And so you would think it would be a good data set to use, but clearly there are some issues to be aware of. So the other thing as well to be mindful of, especially when you're using data from multiple sensors, is that changing sensors can have an impact. So this is again from my colleague at IPMA, Sophia. And so these are differences between MSG, LST, it's that second generation from Severi, different Severi instruments. So each Severi instrument is coloured in a different colour. And you can see particularly in this bottom plot, I think, where she's compared all the data to ERA 5 skin temperatures, that some of the data seem to be misaligned, especially MSG4 there down at the bottom in red. And this is simply because of changes in sensors. Even though they are supposed to be the same sensor, designed by the same people, built probably by the same people, there are differences, and we need to be mindful of these when using data for climate applications. And finally, I think this is pretty much my last slide, I think. This is nothing thermal at all, but I just like it. It's a good piece of work that we're doing at the moment, looking at sunshine duration. So this is, I wanted to use this plot because I think it makes a very important point. So if you look at the top, satellite observations of sunshine are shown in red, and our gridded UK sunshine duration is shown in blue. And these are the anomalies. Again, so this is different from the difference from the long-term average. You can see they agree quite well. You think, yeah, that looks pretty stable, everything's going well, but then you look at the difference between the anomalies, and we see that there are some very clear discontinuities. So the first thing to notice is that we have two volcanic eruptions, which have clearly caused some anomalies, probably in both the in situ and the satellite data, I think here, and they have changed that relationship. So the satellite data tend to be sunnier than the in situ data. We're not quite sure which is more wrong, but I suspect both are probably a bit wrong. We know, for example, that volcanic eruptions like Mount Pinatubo, for example, we know very well that affected radiation measured by ATSR1, which is essentially it's used for LST retrieval potentially. So this is something to be bear in mind about retrieval errors as well. And then I also wanted to point out this other change here, which is where we can very clearly see change from MVERI, which is an older version of SEVERI on MSG. And you can very clearly see where SEVERI has kicked in more recently, because SEVERI tends to be sunnier than the in situ data compared to MVERI, which was the sensor that predates it. So there's some really important things I think to remember. So, one other thing. So my key message really is check the stability. If you're using data for climate, please do this before you do anything else. On the left here is a plot by Abby Waring, who's here today and speaking again tomorrow. And on the right is from an earlier study that we did over Europe, checking stability of the LST CCI data sets. So the top one there is Modus Aqua. What we did there is we compared Modus Aqua observations. Actually, these are anomaly differences there that are shown against in situ data that have been homogenized. So these are corrected for non-climatic effects. So they should be stable over time and therefore giving us a stable reference. And you can see the Modus data that there's very little trend there, if anything. And we consider this data set to be a very stable data set for Modus Aqua, noting this is for Europe, not necessarily applicable to the world. You can see at the bottom here, this is Carlos's LST data based on microwave observations. And you can see, again, it's anomaly differences, a reference to the station data. You can see there is a small jump between F13 and F17. So despite Carlos's best efforts to adjust for overpass time differences and differences between sensors, there's still a small residual effect. But what's important to note is that trend is still less than the GCOS target that we're aiming for of 0.3 Kelvin per decade. So it is still a useful data set, but you need to bear in mind there is this jump. Interestingly, when we look at the stability of each of F13 and F17 separately, they actually are more stable individually. So, and then, as I said, is Abby's latest version of a difference between MODIS and CRU10. This is the station data set I talked about earlier. And this is a global analysis because we've done this because with the camel emissivity problem that we really wanted to check the stability on a global scale. And you can see that this is a very stable data set overall, which is very encouraging. And we're finding this as some of our other data sets from LSTCCI are looking pretty good. And observational coverage also, I think this is my last slide apart from summary. So satellite data, I think people forget you don't get 100% observations. Top plot on the right there is microwave observations, considered all sky. There are still gaps, sometimes due to precipitating cloud, but not often. But there are still gaps between the overpasses. Bottom example there is from Sentinel-3A SLSTR. And you can see that there are a lot of gaps. And this is really important to remember when you use data for climate studies, they are not spatially complete. You are not looking at everything. We have missing data. And this is fine if you consider that. And this plot here is created by my colleague Carlos again. This is the average coverage over MODIS, I think 5 kilometre MODIS data between 2013 to 2021. Generally shows that we're only getting about a 50% coverage. So we're only getting observations one every 2 days, basically, from infrared data. So this is really important to remember when you're doing your analysis. Obviously, like places like Brazil and the Amazon rainforest, we get very, very few observations, if at all. And the other thing, of course, is that it's a snapshot. As Martin mentioned earlier, it is a snapshot at the time of the satellite overpass. So concluding remarks, satellite LST can be used for many applications. There's lots of applications I've not talked about. You've heard lots about them, I think, in this workshop already. Some examples are listed there. Very important, LST is not the same as 2 meter air temperature. There can be very large differences that vary temporally and spatially. Very difficult to predict it from LST. My personal opinion is that anomalies are probably the way forward here because there's a good relationship there. And my main message I want to say, if you're using satellite data for any climate applications, any satellite data, please check the stability or check the literature for reports on the stability, because this is really important, as well as the accuracy. And this should always be step one. And bear in mind, of course, that there are gaps in the data. So, and that's my final point there. Thank you.
Lizzie.
Thank you very much. Hi, Lizzie. Thank you very much for that really interesting presentation. I got 2 questions if we have time for them. First question is, all the plots that you've done, when you mentioned satellite data, is that the CCI data sets or were you looking at any others?
It's a mixture between glob temperature, which was the precursor to LST-CCI. Some of the plot, I think all the plots apart from Abby's plot that I showed are from LST-CCI phase 1. So those data are publicly available through the ESA data portal. We have new and improved versions we are producing now. Some of the other data were from glob temperature.
Right.
Yeah.
Latest version of MODIS.
Okay, and that includes the one where you were comparing with the camel data sets?
Yes, that's the recent CCI data, which are not publicly released yet. Yeah.
All right.
That analysis was from those data, but actually the camel emissivity is used in the version 1 product, so there are issues there that we have become aware of.
Okay, well, hopefully our algorithm team will work on that. I'm seeing a dichotomy here between two statements you made. First off, you said that land surface temperature data sets can vary massively with land cover change, like that mowing example.
Yes, absolutely.
And yet at the same time, you say that the anomalies when subtracting the long-term trend correlate really well when looking at the... So does that mean your climate, your in-situ air temperature stations are located in places where you know the land cover hasn't changed?
So I can't speak for other countries, but in the UK, we are very careful about where we site our stations. We do have to move them sometimes. We try and correct for those effects. So I think the thing I'm saying there is that yes, LST and air temperature are very responsive to land cover change, but the overall signal that you're getting anomaly from the long-term averages should be very similar. So if you get an area that's dried or been devegetated, the LST anomalies will increase relative to the background climate, but the air temperature anomalies will increase as well.
Right. So you were comparing grid cell to grid cell, not the individual state, taking the nearest pixel to the individual.
As well.
Okay.
Yeah.
Okay, cool. Thank you.
Yeah.
I actually have a very quick question. I was really surprised to see such a difference between this camel version 2 and 3. What was it that changed between the versions?
I don't know because I'm not involved with the production. I don't. Mike's shaking his head as well.
Oh, okay.
But we didn't. I mean, it's a well-used, well-known data set, and we were really surprised to find this. But we do think because the stable LSTCCI data I showed from the paper I published was over Europe, and we think the problem is over arid and semi-arid regions. So the LSTCCI products over other areas should be fine, but it's arid and semi-arid that may have an issue.
Interesting. Thanks.